similar to Mark and Rich, we also got we are also extending on last year's talk by Ali on black box testing for Stratum enabled switches. So, so yeah, we'll quickly go over the introduction, which is basically some deep dive into what Ali talked last year. So here, we are trying to achieve a set of vendor agnostic tests to certify a switch as Stratum compliant. And yeah, and in this talk, we are also going to show a basic runner that we have developed to execute the tests in test vectors. And we are trying to use black box methodology for running the test vectors. The reason being, since Stratum is being deployed on various switch vendors, and it's really costly to develop vendor-specific tests. And also the data-driven tests. We are using data-driven tests as a way to define the test vectors, because using that we can use a minimum test runner that can drive through the test vectors and give us the results. One advantage of this is test runner logic will be really minimal, so that we can focus all on the test vectors and not really maintaining the runner. And our device under test is obviously switches that are running Stratum. And along with that, since the Stratum open APIs, GNMI, GNOI, and P4 runtime are available, and they can be used on other switches also, so we can run the test vectors on those switches too. So here is an overview of test vectors. The one key factor of test vector is it separates the test definition from test infrastructure. So different vendors can use different frameworks, programming languages, preference. So if we can define test vectors in a simple manner that anyone can adapt, that helps to develop the vendor agnostic tests. So you can see test vectors is a compact way of defining test input and output. So the test vectors is basically a set of test cases. In this scenario, we can think of them as substeps of an end-to-end scenario. And these are basically actions and expectations. Actions are the open API accesses, the P4 runtime, GNMI, GNOI accesses, or some external stimuli like data plane events or some port events that we want to run against the switch. And these actions change the state of the switch. And to verify the actions, we use the expectation, where the expectations are just the expected behavior after running the actions. And how are we trying to achieve the black box testing with test vectors? So basically, a set of test vectors can be fed into the test vector runner, which so these test cases can then be converted to P4 runtime, GNMI, GNOI calls, or if there are data plane packets that we want to verify, we could possibly connect a separate traffic generator that is connected to the switch under test, or we can also have traffic generator as part of the test vector runner. So how do we generate the test vector repo? It could be human, handwritten test vectors, or we could use some test vector generators to generate the test vector, or for vendor-specific scenarios, even vendors can contribute to the test vector repo. The input for the test vectors are the P4 specs or P4 info, or topology info like chassis config, from which we can get different interface information. Or like Stefan talked before, we can also use SDN controller trace to generate traffic to test regress. Let's go with the test vector details. So like I mentioned, we have actions and expectations before. So I'm going to talk more about the structure of test vectors here. So the test vector definition is already open source with Stratum, and these are coded using protobufs. Since GNMI, GNOI, P4 runtime, the interfaces that Stratum is using are already using protobuf, it gives us a way to reuse those in the test vector definition. Using a proto compiler, we can generate language-specific source code to generate classes for those test vectors. So the proto compiler can generate Java code, Python code, Go code for the test vector, so that you can also implement runner. If you're familiar with protobufs, you know that there are three different different type of attributes in protobufs. There's an optional attribute, which in this case we are for test vectors we are using it as one-time attribute, and here we represent it with single arrow and one-off attribute. So in certain attributes there are multiple sub attribute, and at most one attribute can be used at once. So to save the memory, there's one-off attribute in protobuf. And some attributes could be repeated multiple times, so we denote that with bold arrow here. So the test vector is run against a single switch. So the target information can have the IP address, port, and other information that is needed to connect to the switch. And each test vector has multiple test cases. And there's a test case ID that we can use for debugging purposes. So if any test case fails, we can check in the logs and easily identify that. So each test case has multiple action groups. So these actions, according to the test vector definition, can be either run parallelly or sequentially or in randomized order. So later you will be talking about it, but we were able to implement the sequential and parallel part of the action groups in our test vector runner. Once all the actions are run, we would like to verify that the system state is as expected. So we have multiple expectations to verify those actions. So various type of actions that are defined in the test vector definition are config operation to send the GNMI set request. So we can set various attributes of interfaces and verify that the set is working fine. And then there's control plane operation. This is to verify the P4 runtime part. So if you want to send some flows or set the forwarding pipeline configuration or even perform the packet out operations, it's defined here. And for management related GNOI operations, we have, and along with these APIs, if we have to test also the external stimuli, like the data plane stimulus, where we are sending traffic to certain ports, and also port stimulus to set a port up or down externally, and alarm stimulus to simulate the alarms on certain GNMI paths. There's also a requirement which we are going to use to run, to verify the timing requirements or other requirements to run the actions. Similar to actions, even expectation have GNMI get request response, and control plane to do the read of the flows that we have written, or packet in operation or pipeline config. And I'm going to come back to telemetry. Data plane we use to verify the traffic is coming to certain port that we are testing. So telemetry is basically to test the subscription part of GNMI. So we have we subscribe to a path on GNMI, and then we have certain actions. So like Mark mentioned before, we have the packet counters. We can subscribe to packet counters of an interface and send some traffic and verify that the packet counters are incremented. So that's where we use expectations. So this is a textual representation of test vector data file. So as you can see, we can have multiple test cases, and each test case can have different action groups. So here there's a sequential action group which is performing a P4 write request, and also there's another action that we are trying to send a packet to port 2. So once the actions are executed, we verify the expectations. So since we have already sent a before write request, we want to verify that the response is coming fine. So we check the expectation, and then we also have the packet verification. Right now, these are the test vectors that we have implemented. We have implemented some P4 runtime, L3 or other packet scenarios that we have ported from PTF. And there are some GNMI test cases. These we have semi-automatically generated based on list of paths that we have. And E2E, the end-to-end scenarios are basically a combination of P4 runtime and GNMI, where we have the subscription and then packet forwarding scenarios. Currently, we support BMV2. We have tested test vectors with BMV2, Barefoot Tofino, and Broadcom Tomahawk switches. To talk about next USD.
So, okay, all right. So I'll talk about the test vector runner details. So test vector runner could be anything that compiles and runs test vectors. But here, what we are talking about is reference implementation that we have been working on. Wait, hello? I guess it works. It works. Hello? Okay. So here what we are talking about is reference implementation of that we have been working on. This slide is giving you an overview of this project. It's written in Go. It's taking advantage of Go testing framework, and it runs with various switch targets, including BMV2 switches and hardware switches. And if you want to switch to a different target, you just need to provide a set of input files to test vector runner. Includes a target file, which defines IPs, ports, and other information that's required to access the switch, and a port map file, which describes how the data plane ports are connected. And then the test vectors could also be different. For example, you have different pipeline config files for different switch targets, and if you're using different ports on different switches, you also need to provide the different test vectors. So in terms of deployment, we provide a Docker file, which simply deploys everything inside a container. And so if you want to test with hardware switches, we also give you a script that you can deploy the test vector binary to external server that has physical connections to the switch. We'll come back to the details of that later. Okay. So you have seen this in the previous slide. I think this diagram is giving you more details of the test vector runner. Basically, the test vector runner reads from one or multiple test vector files and compiles that with an orchestrator by processing various actions and expectations. And eventually, depending on the types of the actions and expectations, it will call various framework modules and to build, send, and receive either gRPC messages or data plane packets. There's also a list of common libraries that's used for logging, gRPC connection management, and packet I/O. Okay, so we mentioned that we use Go testing framework. So how do we map test vectors to Go tests? According to the definition of test vectors, test cases are the smallest testing unit, and one or more test cases compose a test vector. And also here we also combine multiple test vectors to a test suite. So basically it's a three-level hierarchy here. The good thing is Go testing also use a similar way to organize the tests. We will be showing some pseudocode here to explain how we map test vectors to Go tests. But basically we use this main function from the testing package, and which takes a slice of internal test. We use that to represent the entire test suite that we run. And then for each of the internal tests, it corresponds to a test vector. And then we use the concept of subtests in Go test to build test cases. Okay, so then for inside each test case and for each action and expectation, there will be a process function to convert the actions and expectations to RPC calls or data plane packet I/O. Okay. So, well, this is not the code that you're going to write. Right? So it's just these mappings will be dynamically generated during runtime. And most of the work here actually goes to the implementation of those process functions. Eventually, we will support all the types of actions and expectations, but we are not there yet. In terms of what we have implemented, and again, we're using this diagram, but the boxes with the solid lines are the operations that we already supported. And the others are the missing parts. I guess I'm going to skip the detail of this due to the time limitation. But it's the same case for expectations. Actually, we have implemented most of this, but there's still some missing parts here. This is an example of running the P4 runtime test suite. As you can see, this test vector runner binary is taking like a path to the test vector files and the target file and pop map file as input, and then it executes all the tests sequentially. In this case, there are 3 test cases, and three tests, and each test is actually a test vector. And you can see inside each test there are subtests, or we call them test cases in the context of test vectors. So this minimum reporting is from GoTest. You might be familiar with this. As you can see, it's printing the test names, the subtest names, the results of each step, and the time that takes to run, and also overall result. So if any of these tests fail, you could always run a single test and increase the log level. So here is another example of running a single test with info level logging. You can see it gives you more details of how we convert test vectors to like P4 write requests, GenMI requests, and packet I/O, and you can see also why it fails. Okay, so as we already mentioned, we currently support 2 deployment scenarios. The first one is to deploy with a single container. So in this case, the container will have a BMV2 switch and the TV runner binary embedded. And inside the container, the TV runner will talk to the switch via both gRPC and virtual Ethernet interfaces. The other deployment scenario here is for testing hardware switches. So this is also straightforward. You will need a server that has physical connections to the switch ports for sending packets. And also in this case, we'll deploy the test vector runner on the server. Of course, it also needs to have gRPC connections to the switch. So we talked about in the beginning, the test vector will have its own repo. So you will need to download test vectors in both cases. Okay, so I think the last item we have is to talk about the next steps of both test vectors and test vector runner. For test vectors, I think the most important thing for next step is automatic test vector generation. What we are currently doing, so the current test vectors we have are either handwritten test vectors or semi-automatically generated test vectors. For example, for most of the P4 runtime test vectors we have, they are manually ported from PDF tests, as Abhilash already mentioned. And we manually modify that for different switch targets. This process is tedious, time-consuming, and it's also error-prone and hard to debug. So, but we also have we developed some tools to help us to generate part of the test vectors. For example, we were able to get Stratum log and extract the P4 write request from that and put that into test vectors. And also we are generating pipeline configs from P4 generated binaries and JSON files. And also for actually most of those GNMI tests, we generate the get operations by reading a list of the supported GNMI path. But still, there are a lot of manual steps involved. And moving forward, I think we definitely need a much larger number of tests. So I think the future plan is to have tools that could generate complete test vectors automatically. So we will have various inputs that we can read to help generate test vectors. Here's just some examples. We could read from chassis config file to learn how the ports are configured, and which help to generate GNMI-related test vectors. And then we could also read from SDN controller trace and convert that to test vectors to just replay the controller operations. And also, as Google just proposed, we could also use this automatic test vector packet generation tool to generate packets and put that into test vectors. Okay, so as for the next steps of test vector runner, I think we're thinking of deploying with more scenarios. We already mentioned that we could deploy in a single container or a server that has connection to the switch. And the third scenario would be to deploy on a single switch. So in this case, the test vector runner will still have gRPC connections to the switch, but since the physical connections are gone, it won't be able to directly send packets to the switch. So in this case, in order to do data plane verifications, we will need to enable a loopback mode on the switch and use packet ins and packet outs to mimic data plane traffic. For example, if we want to send a packet to a specific data plane port, and we send a packet out instead, and then when it reaches that port, it will loop back, and then from there, it will be processed by the pipeline in the same way as a normal data plane packet. And let's assume that it's forwarded to another port, and then it loops back again, and eventually it will be forwarded back to the TV runner as a packet in. So I think in this way, we should be able to run the same set of test vectors as the other scenarios. But the only difference is that we just need some extra processing for the packet ins and packet outs. But that should be handled internally in the test vector runner, and we don't need to touch the test vectors. Okay, so, and the last scenario would be to deploy with some external traffic generator. What we are currently doing is the traffic generator we're using is actually part of the test vector runner with our current implementation. I think that satisfies like some basic data plane testing scenarios, but for more advanced scenarios like high-speed packet generation, we will need external traffic generators. So in this scenario, the traffic generators will be connected to the switch, and we will need to find a way to translate what we specify in test vectors to what the traffic generator can understand. Okay, so I think we use this is our last slide. We use this as a summary of the next steps and also a call for help from the community. For test vectors, I think the most straightforward help that we need is to build more test vectors. So handwritten test vectors help, but if you're interested in building tools that automatically generate test vectors, that would be even better. As for test vector runner, as we mentioned, the first thing is to support the missing operations, like for the various actions and expectation types. And the other thing is to support deployment in more scenarios, like single switch deployment and deploying with external traffic generator. Okay, so I think that's all we have. We will open source our code, I think soon after ONF Connect. But if you're interested to help us to reach the open source stage, you could either join us on the Slack channel or just send us an email. And the last thing is, if you're interested in seeing a live demo of all we talked about today, just visit the Stratum demo booth. Thank you.
We have time for a few quick questions.
May I ask what kind of traffic generator you're using? Is it open source or is it Google proprietary? Or
so you mean the traffic generator we are using currently?
yes.
Oh, it's part of the test vector runner. So it's written in Go. It's using that Go package. It's just a simple module to send and receive packets.
So you say you're going to open source the test environment, so it will be including, it will commit to a GitHub or something?
Yeah. It will happen. So.
Okay. Thank you.
Yeah, it's worth asking. So this is one of the first times I've seen like a GNMI tester. If I did not have, so let's say that we didn't have P4 runtime implemented, but still wanted to utilize that to verify GNMI functionality, would that still be a use case for test vectors? Just purely GNMI verification and stuff?
Yeah, you could still use test vectors for purely GNMI tests also.
Other questions?
So you have the test scenarios 1 to 3, right? And test 1, those are the same test coverage, or there are different test coverages. What are those? I mean, do you know what I'm saying? Yes, I mean the test scenarios 2, scenario 3, scenario 4, they're the same test coverage, right? Or different test coverages?
It could be same test coverage, but there is different ways to run the test.
Just different test
deployment scenarios. Yes, that's.
I mean, the biggest difference in these three is the first one you're using the server to generate traffic, the second one you're using packet ins and outs using loopback, and the third one you have an external traffic generator. Yeah.
But test case is the same things. Okay, thank you.
Yeah, I mean, there's certain tests that you couldn't run at like high-speed data plane port packet generation. It would be hard to run in scenario 3, whereas it might be easier in 4.
Thank you.
Other questions? No? Let's thank our speakers.